Congratulations, you've made it to the end of your introduction to vector algebra. We've covered quite a bit along the way, and now you should be ready to move on and use vector algebra in a variety of applications. In this final lesson, we'll go through a brief, big picture recap of everything we've covered. The goal is to help you amalgamate all of the bits and pieces into a single coherent picture. We started out with vector basics, where we learned what vectors are, how to represent them, and how to conduct some basic operations on them. At the end of this section, we were able to recognize vectors, distinguish them from scalars, combine them through addition and subtraction, and scale them through scalar multiplication. We saw that the basic operations were valid for both vectors in the magnitude direction representation and in the components or unit vector representation. Those two different representations could cause some problems for us if we have data in different forms. To get around this problem, we learned how to convert from the magnitude direction representation into the components or unit vectors representation, and vice versa in 2 dimensions. Then we looked at how magnitudes and angles could be determined for a 3-dimensional vector. That meant that we could represent a 3-dimensional vector as a magnitude multiplied by a unit vector in the direction of the original vector. Closely related to that off-axis unit vector is the idea of direction cosines, which give us information about the angles between the vector of interest and the coordinate axes. Once we had an understanding of vectors, vector representation and conversions, and basic vector operations, we were ready to start looking at multiplying vectors by one another. We started with the dot product, which is also known as a scalar product because the result of the operation is a scalar. We learned what the dot product means and how to calculate it from vectors either in the magnitude direction form or in the unit vector representation. In the process, we saw a couple of useful special cases, and we discovered that the process is not invertible. In other words, there's no such operation as dot division. We also saw that the dot product can be a useful tool in analyzing the geometry of vectors. We saw that it can be used to help us find a vector magnitude, angles between vectors, and both the scalar and vector projection of one vector onto another. After all that, we looked at the next type of vector multiplication, which is the cross product, also known as the vector product because the result of the cross product is a vector, specifically a vector that is perpendicular to both of the input vectors. As with the dot product, we learned what the cross product means and how to calculate it from vectors in both the magnitude direction representation and the unit vector representation. In the process, we discovered the right-hand rule and saw a couple of useful special cases. We also discovered that as with the dot product, the cross product is not invertible, so there's no such operation as cross division. After we had an understanding of what the cross product is, we looked at some mnemonics to help us remember the cross product formula. Those mnemonics were the determinant and the cross product matrix. So we have 3 tools for calculating the cross product. We have the cross product formula, we have the determinant, and we have the cross product matrix. They all provide the same result, so which one you use is up to you. Both the dot and cross product show up in applications in a variety of STEM subjects. Sometimes they show up together in the form of a triple product. A triple product is simply a single term consisting of 3 vectors multiplied together either with 2 cross products or with a dot product and a cross product. In the case of the scalar or mixed triple product, which consists of a dot product and a cross product, we saw that the resulting product could be interpreted physically as the volume of the parallelepiped defined by the 3 input vectors. We also saw that the order of operations was defined by the fact that we can't cross product a vector with a scalar, so the cross product has to be executed first. One of the rules that we saw applied to the scalar triple product was the rule of cyclic shifting, which tells us that we can change the order of the input vectors cyclically without changing the final result. Finally, we saw that the shortcut way to solve a scalar triple product was to use the determinant and fill it with the components of the 3 input vectors. When we moved on to the vector triple product, we saw some key differences. The most obvious one was that the final result of the operation is a vector. Also, we saw that the order of operations is not defined by the operations themselves, so we require a set of parentheses in order to define a unique solution. If we're looking for a shortcut to solve the vector triple product, we have the back-cab theorem, which allows us to re-represent the problem as a pair of dot products followed by a pair of scalar multiplications. Now that you have a foundation in basic vector algebra, you're ready to apply this knowledge to a variety of science and engineering applications. You also have a jumping off point to start learning more about vectors. For example, you might want to learn about linear algebra, which includes the use of matrices to operate on vectors of any number of dimensions. You might also want to learn about vector calculus, which involves the differentiation and integration of vector functions. Whichever direction you choose to move in, the material you've learned in this course will give you a strong foundation to build on. So good luck in the future and enjoy your chosen path with vector algebra.